Hello YouTube. So a little while ago I did a couple of videos on laws of nature, and in those videos I introduced two ways of thinking about laws of nature: regularity theories and necessitarian theories. In this video I'm going to introduce a more sophisticated version of the regularity theory, David Lewis's best system analysis. So laws of nature, well, these include principles such as nothing accelerates beyond the speed of light, or the net force on a body is equal to the body's acceleration multiplied by its mass, or heat always flows spontaneously from hotter regions to colder regions. Now, of course, these might all be mere approximations. The story of science is not yet complete. No doubt some of the principles we currently take to be laws will be overturned or modified, but, those sorts of things are the kind of things we have in mind when we talk about laws of nature. What exactly is it for something to be a law? Well, as I mentioned, broadly speaking, there's two approaches to this. So, as I said, I've talked about this in earlier videos. I'll put those in the comments, but just to give a brief outline of the background here. So, regularity theory, sometimes called Humeanism after David Hume, holds that laws of nature are nothing more than universal regularities in the world. A law is just a collection of its instances. So to say that it is a law that nothing accelerates beyond the speed of light is just to say that, in fact, nothing accelerates beyond the speed of light. There are no objects that do that thing. So on the regularity theory, the laws tell us how the world in fact behaves. According to necessitarianism, laws of nature are more like principles that govern the events and processes in the world. For it to be a law of nature that nothing accelerates beyond the speed of light means that there is some sort of governing principle that necessitates that no object exceeds the speed of light. So for the necessitarian, the laws tell us not just how the world in fact behaves, but how the world must behave. There is genuine physical necessity. So one way to put this is that for the regularity theory, what the laws are depends on what the local facts are, right? Laws are just true generalizations about what happens. For the necessitarian, what the local facts are depends on what the laws are. Laws govern what happens. Laws make it the case that what happens is what happens. So again, you can see my earlier videos for a more thorough introduction, but hopefully that sort of sets up the general idea there. So the best system analysis is defended most notably by David Lewis, and this is, as I said, a version of the regularity theory. Now, Lewis's background assumption here is an approach to metaphysics known as the Humean mosaic. So, as Lewis puts it, the Humean mosaic is the doctrine that all there is to the world is a vast mosaic of local matters of particular fact, just one little thing and then another. Essentially, there is nothing to the world beyond the intrinsic properties of fundamental particles, so properties like mass and charge, plus their spatio-temporal relations. Everything else is grounded in this. All the truths about laws and causes and dispositions and powers and so on are reducible to the arrangement of these local particular matters of fact. Now, since Lewis holds that everything reduces to the distribution of properties in the Humean mosaic, he has to reject necessitarianism. Ultimately, there are just the matters of fact about the Humean mosaic. There are not, in addition to the objects and properties in the Humean mosaic, there are not also laws that sort of stand outside the Humean mosaic and that govern the Humean mosaic. If there are laws, then they have to just be regularities in the Humean mosaic. Again, I have a video on the Humean mosaic. I'll link that in the comments. So that's the background, right? This is the sort of background this just kind of gives the context to this best system analysis. So with that said then, let's turn to the best system analysis. So one of the central challenges for any regularity theory of laws is that not every regularity is a genuine law. Some true generalizations, such as no object accelerates beyond the speed of light, or all electrons are negatively charged, or no mountains are composed of plutonium, those sorts of generalizations are law-like, but there are other true generalizations that are not. So, no mountains are composed of gold, or all the coins in Cain's pocket are copper. Those are true. These are true generalizations, but they're not law-like. They're not laws. I mean, we want to say that it's not just that no mountains are composed of plutonium, but that there could not be mountains composed of plutonium. You know, if you put that much plutonium together, you get a nuclear explosion, not a mountain. On the other hand, although there are no mountains made of gold, in principle there could be. Nothing prevents that from happening. So, what exactly is it about the Humean mosaic that makes a true generalization into a genuine law of nature? Like, how do we distinguish the genuine laws from the mere accidental regularities? So, the basic idea of the best system analysis was actually stated by Frank Ramsey. So he says that the laws are consequences of those propositions which we should take as axioms if we knew everything and organized it as simply as possible in a deductive system. So the idea is that a theory of the world can be expressed in a set of statements. The laws of nature are those statements that give us the largest amount of information about the world in the simplest possible terms. So in other words, suppose we are given the task of stating as much information about the world as we can in a description that is as simple as possible. What would we want to include in that? Well, I mean, surely, we'd probably want to include facts about, space-time, light, gravity, mass, fundamental particles, that sort of stuff would be worth mentioning. We'd want to include the fact that, all electrons are negatively charged. Electrons are among the basic constituents of the world. They occur everywhere. They play important roles in almost all of the phenomena that we observe. And we can make various inferences about other phenomena from the way that electrons behave and so on. Like, electrons are everywhere. They're clearly important. So we want to know that all electrons are negatively charged. On the other hand, it doesn't seem like there'd be any point in explicitly stating anything about the character of the coins in my pocket. Those coins are maybe relevant to me, they're located near me, and that's about it. They have no significance for anything else, and knowing information about those coins doesn't really tell us anything about the world in general. So there are, as a matter of fact, numerous true deductive systems. There are numerous sets of propositions that can be axiomatized. Some of these sets of propositions are simpler in the sense that they can be axiomatized using fewer propositions. Some of these sets of propositions are stronger in the sense that they contain more information. The laws of nature are the axioms of the true deductive system that achieves the best balance of simplicity and strength. So that is, it's the theory that uses as few axioms as possible to accommodate as broad a range of particular matters of fact as possible. So more precisely, Lewis asks us to consider a system for describing the world. What do we want it to look like? Well, Lewis says it must be entirely true, it must be closed under strict implication, it must be as simple in axiomatization as it can be without sacrificing too much information content, and it must have as much information content as it can have without sacrificing too much simplicity. A law is any regularity that earns its inclusion in the ideal system, or in the case of ties, every ideal system. So we have to consider So let's consider various systems of true propositions about the world, right? So one set of propositions might contain the following. So it might contain, this aluminium rod expands when heated. This sample of mercury expands when heated. This brass key expands when heated, etc., etc., etc. So we could just sort of imagine this list of propositions for every metal that there is. And then you can imagine another set of propositions that says, all metals expand when heated. Now, notice that these propositions communicate the same information. I mean, at least, so given the auxiliary assumption that aluminium, mercury, brass, etc. are metals. So if we sort of take these sets of propositions along with the auxiliary assumption that aluminium, mercury, brass, etc. are metals, then they contain the same information because the former set of propositions can be derived from the latter. Since we know that these things are metals, and since we know that all metals expand when heated, well, we don't need to explicitly state for each sample of these metals that those samples expand when heated. So we have, we've sort of simplified, right? We have the same information content, but it's simplified in the second case. Similarly, there are many facts about the relationship between force, mass, and acceleration in particular contexts, but we can cut out all those, we don't have to state all those specific facts, we can just state the generalization that force equals mass times acceleration. So this should give you a sense of what it means to have a sort of simpler theory and what it means to state the information. Why do simplicity and strength matter? Well, as Lewis sees it, these are simply the normal standards for theory choice within science. It's obvious why strength is important. We want our theory of the world to tell us about the world. We want it to give us information. Otherwise, what would be the point of theory construction? If we didn't care about having information about the world, we might as well write fiction. As for simplicity, well, this is important because human beings are cognitively limited. We need to be able to use our theories to make predictions and build technologies, and this requires theories that are simple enough for us to comprehend. Moreover, simple generalizations that capture a great deal of information allow us to unify various phenomena that might initially have seemed disparate. So we can appeal to electrons when explaining phenomena such as lightning and thermal conductivity and the solidity of a table and nucleosynthesis and stars and all of that. All of these seemingly disparate phenomena can be unified under one conceptual scheme. So one issue, though, of course, is that simplicity and strength often pull in different directions. A description of the world that is maximally strong would just be a list of all the true propositions. Clearly, a list like that would be just utterly unwieldy. It wouldn't also give us any way of grounding a distinction between the laws of nature and other propositions, between laws and accidental regularities. The simplest possible description would presumably just be nothing at all. What we need is a system that provides lots of information about a wide range of phenomena, but where this information can be stated in a short set of propositions. And on this basis, we can order the various true sets of propositions about the world, and hopefully one will come out on top. So from the Humean mosaic of just particular matters of facts, we can derive the laws as the axioms of the best system for describing that mosaic. So recall that one of the central challenges for any analysis of laws is to distinguish between laws and accidental regularities. There are no mountains made of gold, but in principle there could have been. There are no mountains made of plutonium, even in principle there could not have been. Even if we created enough plutonium, we could not put that much of it together. So how do we account for this difference? Well, the best systems analysis has a simple answer. The laws are those generalizations that are the axioms of the best system. So if you take a true generalization, such as all the coins in Keynes' pocket are copper, well, okay, that's a true generalization, but we wouldn't add it to the best system. It provides very little information about the world. It detracts significantly from the simplicity of the system. On the other hand, we would want to include certain generalizations about plutonium and gold, in particular that plutonium is highly radioactive and gold is not. These generalizations, in conjunction with certain other principles about energy and nuclear reactions and so on, will entail that there are no plutonium mountains. They will entail that such a large mass of plutonium would result in a nuclear chain reaction, but they will not entail that there are no gold mountains, right? They're not going to entail that a large mass of gold will result in a nuclear reaction. So along similar lines, one criterion for lawhood is that laws should support counterfactuals, whereas accidental regularities should not. So it's not just that all plutonium happens to go critical above a certain mass, but that if I had created a large mass of plutonium, then it would have gone critical. Now, Lewis views the semantics of counterfactuals in terms of possible worlds. So the counterfactual, if P had been the case, Q would have been the case, means something like, in the closest possible worlds in which P is the case, Q is the case. The closest P worlds are Q worlds. So the claim is that in the closest worlds in which I create a large mass of plutonium, the plutonium goes critical. Now, the question is, what exactly are the closest worlds? Well, one criterion is that, they're worlds that have the same laws as ours. For Lewis, this is cashed out in terms of patterns of regularities that obtain in those worlds. The closest worlds will be worlds in which the Humean mosaic has a very similar arrangement of properties. I mean, that's really what it is for a world to be close, right? When we talk about close worlds, we're talking about similarity. The closest worlds are the most similar worlds. So, of course, since ultimately all there is the Humean mosaic, the closest worlds will be those worlds that have a similar arrangement of properties in the Humean mosaic, such as, for instance, the large masses of plutonium sustaining nuclear chain reactions. So that's to say that the axioms of the best deductive systems for describing those worlds will be the same as the axioms of the best deductive systems for describing our own. Now, if we take something like all the coins in Kane's pocket are copper, well, consider a world in which we place a silver coin in Kane's pocket. Does that coin become copper? Right? Will it be true that, if we had placed the coin in Kane's pocket, it would have been copper? Well, no. The world in which we place a silver coin in Kane's pocket and it remains silver is much closer to our world than a world in which we place a silver coin in Kane's pocket and it spontaneously transforms into copper. If that kind of thing was happening regularly in a world, well, clearly we would be dealing with a world in which the arrangement of properties in the Humean mosaic would be very different indeed. So the axioms of the best deductive system for describing that world would be very different from the axioms of the best deductive system for describing our own. So, this does something, hopefully, to explain, so basically the counterfactual, if we had put the silver coin in his pocket, it would have become copper. That's going to be false. So, yes, there is so it's true that all the coins in Kane's pocket are, oh, I just messed up that example, didn't I? Sorry about this. I've just realised that what I did is that I switched what's going on in the actual world from all the coins in Kane's pocket being copper to all the coins in Kane's pocket being silver. Or did I do that? Yeah, I did. Where it says the regularity that all coins in Kane's pocket are silver does not support the counter. That should say the regularity that all the coins in Kane's pocket are copper does not support the counterfactual. That's what that should say there. I guess this is the kind of thing where somebody who's more professional and sophisticated would go back and edit and all of that. I'm not going to do that. I'm just going to plow straight on and hope that you get the point. I should note that this discussion is highly simplified. Lewis had a lot to say about counterfactuals. Hopefully this illustrates how the best system account can draw a connection between laws and counterfactuals. Now, one of the very unfortunate laws of our world is that all human beings have to put food into their mouth in order to survive, and food costs money. So if you would like to keep me alive, if you'd like to help Kane stay alive, then you can sign up to my Patreon. You can give me some cash, and there are bonus videos on my Patreon. I upload bonus videos about once a week on there, so there's more content there. The average is about 20 minutes long, so there's a whole bunch of extra content available on my Patreon. So sign up to that if you're interested in that. I would really appreciate it. You can also just give me a one-off donation on PayPal. I offer private tutoring in philosophy. I have a degree, a master's, and a PhD in philosophy, so that's my background. And there's also a Discord, which, links to all of this will be in the description. Okay, so let's turn to some problems for the best system analysis. Now, an immediate problem was noted by Lewis himself, which is that the same set of regularities can be described using different languages, and those languages may differ in terms of their simplicity. So, in particular, here's a problem, right? We can express the content of any system whatsoever in the following way. So, for any system S, we can define the predicate F to apply to all and only those things at worlds where S is true. So, basically, we can then take F as a term of our theory, and we can axiomatize S as for all X, X is F. In other words, everything is F. That's extremely simple, but that's going to work regardless of what we take as S. S can be Aristotelian cosmology, or Newtonian mechanics, or quantum mechanics, or anything else, right? We just take some theory, we consider the worlds in which that theory is true, and then we say, well, F is the predicate that applies to all and only the things at those worlds. So everything is F will then express the total content of S. So in other words, suppose that we just gave a list of all of the facts about our world. That list would not be simple. It's an infinite list of propositions. Well, we can call that list S. And then we can say that the predicate F applies to all and only those things at worlds where S is true. So basically, we can now axiomatize our infinite list of propositions as everything is f. For all x, x is f. And so now we have an extremely simple theory that is also maximally strong. And of course, this looks like it's going to just trivialize Lewis's analysis of laws, right? By employing this kind of abbreviation, we can make any description whatsoever extremely simple. I mean, obviously, look, intuitively, this feels like the simplicity is achieved through a linguistic trick, but what exactly has gone wrong here? Well, I mean, clearly the problem arises because we're assuming that it's legitimate to use predicates like f when stating our system. So the best system analysis is going to require some constraints on what counts as an acceptable vocabulary. I mean, there are independent motivations for such constraints, because you might say, well, what exactly does the predicate f actually mean? I mean, you're not going to understand the meaning of f unless you already have a prior understanding of the theory S, where that prior understanding is going to be couched in much more complex terms. So if S is in fact just an infinite list of propositions, well, in order to understand what F means, you're going to have to understand that infinite list of propositions. So, you might say, well, in practice, of course, we can't really take F as being a primitive, right, being a primitive term. But still, I mean, this sort of illustrates this worry, right? This worry that, well, whether or not whether or not some system counts as simple just kind of depends on the language in which we use to state it and what terms we take as primitives. So we need some sort of constraint on vocabulary. And Lewis proposes a very important constraint. So he appeals to what he calls perfectly natural properties. So he says, let the primitive vocabulary that appears in the axioms refer only to perfectly natural properties. What are perfectly natural properties? Well, unfortunately, it's not possible to give an uncontroversial definition, but hopefully I can communicate the idea. So, natural properties are those properties that carve nature at its joints. It's easiest to see this by just, making a comparison, right? So let's compare some sets of properties. So we have properties like being an electron, negative charge, gravity, right? But compare these properties with properties like being a chair, or being an enjoyable movie, or bitterness. So that the former set of properties are more natural, they're less gerrymandered, they're less dependent on human perspectives and concerns. So the idea is that we can sort of rank properties by their naturalness, by how much, we have this sort of class of things, right? And some classes of things are objectively more similar than other classes of things, and some classes of things are kind of grouped together only because they happen to play some sort of role in human life, right? Whereas negative charge, well, that's things that are negatively charged have like this objective similarity. Things that are chairs, not so much. Being a chair is more just a matter of something that's maybe relevant to human beings in particular contexts, and that's about it. I mean, note that one of the achievements of science consists in its classification schemes. I mean, you might sort of think that classification isn't really that important, right? And what does it matter what we call things or how we group things together? Well, it turns out that actually in science it matters quite a lot. I mean, consider how something like the periodic table encapsulates so much of our knowledge of chemistry. The periodic table expresses various objective distinctions in the world. It captures objective relations of similarity and difference. Or consider debates about what counts as a planet. The definition of planet has changed a great deal over time as our understanding of planets and other astronomical objects has increased. So, a lot of scientific knowledge seems to be expressed in how we classify. Now, classification is, in the end, up to us. We find certain classification schemes more or less useful, but, why are some of them more or less useful? Well, Lewis would say it's because some of these schemes do a better job at tracking the natural kinds. Our knowledge of astronomical phenomena is expressed in our classification schemes. We group like things with like things, and whether or not two things are alike is not up to us. It's an objective property of the universe. There are objective similarities and differences. So the perfectly natural properties are the fundamental properties of physics. The properties of the fundamental particles or fundamental entities, more broadly speaking, even if they're not exactly particles. Other properties can be more or less natural. The periodic table is a very natural classification scheme. The Morgan-Keenan system for the classification of stars, well, that's rather less natural. In this case, there are no strict boundaries between the different classes. There's just a sort of spectrum of different stellar types rather than a strict division. Whereas, like, you know, in the case of the periodic table, there's a strict division between hydrogen and helium. There's nothing in between hydrogen and helium. Whereas when you look at the Morgan-Keenan system, between O-type stars and B-type stars, well, there's no strict division there. There's just like a gradual increase in mass, a gradual change in the spectral properties. Color classifications are less natural still. There are a variety of different physical processes that produce the color blue, for instance. Right? Blue might be produced by a source of monochromatic light of 500 nanometers. It might be produced by compounds of copper. The blue of a person's eyes is produced by Tyndall scattering. The blue of the sky is produced by Rayleigh scattering. The only thing that really unites all blue things is that they appear a particular way to most normal humans under specific conditions. Had human beings evolved with slightly different visual systems, we would never have recognized the property blue in our theories of the world. Hopefully you can see that this is where this idea of sort of more or less naturalness comes from. We don't yet know the complete story about the fundamental physics of the world. One day, hopefully, we will know that, and that story will tell us what the perfectly natural properties are. For now, properties like mass and charge and spin are, I guess, the best approximations. That's as close as we've got to figuring out what the perfectly natural properties are. So, the fundamental laws of the world must be stated in terms of perfectly natural properties. This means that, strictly speaking, the fundamental laws of nature are they're the only laws, right? The fundamental laws of nature are only the laws of physics. The laws discovered by by other sciences are derivative from these. But that seems, I guess a lot of people would say, well, that seems like the right result. The history of science has been a history, to a large extent, of reduction to physics. We learn how things work by learning the parts of which they were composed and the causal mechanisms that govern those parts. In modern science, there seems to be a pretty strong methodological principle that any theories in the special sciences be compatible with the discoveries in physics. There are no genuinely emergent phenomena. So, insofar as we talk about laws in the special sciences, we're sort of talking in a derivative sense, right? The fundamental laws are the laws of physics. Now, with that said, we can see what went wrong with the F predicate. Fness is not a perfectly natural property. It's a highly artificial property. So, the complete statement of the best system analysis is: the laws of nature are the axioms of the system of truths that best balances simplicity and strength, where the predicates used to state those truths refer only to perfectly natural properties. That is the basic idea. Okay then, so one of the most pressing objections to the best system analysis is the subjectivity problem. And the underlying assumption here is that laws of nature are supposed to be objective. They're supposed to be mind-independent features of the world. What the laws are should not depend on what we believe or what our interests are or what language we use or anything like that. The laws are discovered, not invented. Now here's the problem. Whether some generalization L is a law of nature depends on whether it is an axiom of the system that best balances simplicity and strength. So L is a law because it is part of the best system. It is the system that makes the laws, as it were. But the trouble is that there don't seem to be clearly objective criteria for weighing simplicity and strength. One part of this is that, as we noted earlier, simplicity and strength conflict. They pull in different directions. So there's a trade-off between simplicity and strength. But how exactly do we weigh each of these things against each other? Well, it seems clear that that's going to depend to a large extent on our interests and our goals. Indeed, so, let's say, for instance, why does simplicity matter? Well, part of the reason is because the complete truth would be hopelessly complex, hopelessly unwieldy, And we want theories that we can comprehend, so that we can apply them to help us predict and control nature. So in that case, when we talk about simplicity, the standard there must be, at the very least, simple enough to be understandable to at least some human beings. So then it looks like what counts as the best system is going to be determined partly by our goals, our interests. It's partly by like our, the limits of our cognition and the goals that we're putting the theory to. Which means that what counts as a law is going to be kind of determined by the limits of our cognition and by our goals and interests. And that's a bit odd. I mean, worse, it's not just that we're weighing simplicity and strength, because there are many different kinds of simplicity, and these kinds of simplicity can come into conflict. So here's a few kinds of simplicity. I'm just taking this from the Internet Encyclopedia of Philosophy. So quantitative parsimony postulates a smaller number of entities or processes. Qualitative parsimony postulates a smaller number of different kinds of entities or processes. Common cause explanations postulate common causal processes to account for disparate phenomena. Symmetry postulates that the laws describing the phenomena are the same from different reference frames or perspectives. And there's a whole bunch more as well. Those are just a few. So then the question is, well, which kind of simplicity actually matters? That's probably going to be quite context dependent. Physics emphasizes symmetries, but that seems to be less important in the special sciences. I mean, again, ultimately scientists are going to, be guided here by practical considerations. There are similar issues that arise with the notion of strength. A theory is stronger the more information it gives us about the world. But now let's compare two descriptions of my arm hair. So the first description tells us in exact detail the precise shape and size of each of the hairs on my arms. This is an enormously complex description. In purely sort of syntactic terms, it provides a great deal of information, enough to fill a large book. The second description gives only an approximate statement of the shape and size of the arm hairs, and it also gives an approximate statement of how the hair grows and what the hair is composed of. So it says that, my hairs are produced by follicles in the dermal layer of the skin. They're composed of 95% keratin. It's essentially the sort of description that you might find in a biology textbook. Now, which of these descriptions is stronger? Well, I mean, it's hard to know where to even begin assessing that, right? Like, which of these descriptions gives us more information? The first description provides detailed information about certain specific properties. The second provides less detailed information about a broader range of things, but which gives us more information? That's just not clear. So Lewis's response to this issue is that, well, while it may be difficult to tell whether one theory is simpler or stronger than another, and while there may indeed be vague cases where it's just indeterminate whether one theory is simpler or stronger than another, even so, there are still cases that are perfectly clear, right? There are cases where one theory is just clearly far ahead of another in terms of simplicity or in terms of information content. So just take like a third description of my arm hairs, which consists only of the proposition, they grow on my arm. Well, that has much less information content than either of the two descriptions that I discussed previously. So, I mean, yes, there are vague cases, but Lewis would say there's still, these criteria are still largely objective. There are some, sometimes somebody might sort of say, well, this theory is simpler than another one, and it just be wrong, like clearly wrong. It's clearly wrong to say that the description, they grow on my arm, provides more information than either of the two descriptions I noted previously. So Lewis grants that there may be different ways of assessing simplicity and strength, but he hopes that given that given that we can recognize that certain ways of assessing simplicity and strength are plausible, we can hope that one theory will be uniquely the best according to any plausible criteria. So Lewis says this: if nature is kind, the best system will be robustly best, so far ahead of its rivals that it will come out first under any standards of simplicity and strength and balance. We have no guarantee that nature is kind in this way, but no evidence that it isn't. It's a reasonable hope, Perhaps we presuppose it in our thinking about law. So that's maybe one line we might take there. I mean, I suppose another point we could make here is just that, even if the standards for simplicity and strength are dependent on our interests and concerns, the laws are still discovered in an important sense. Our standards for simplicity and strength, whatever they may be, will apply to the various sets of true propositions about the world. Given a certain standard of simplicity, there will be a fact of the matter whether some system meets that standard, even if we haven't yet conceived of that system. So we set the relevant standard for simplicity, but then we discover whether or not a system meets that standard. So, should we care about quantitative parsimony, the mere number of entities in the world? Well, maybe there's no objective fact of the matter about whether we should care about that, but assuming we care about that, it is an objective fact that a theory that postulates a finite universe is more quantitatively parsimonious than a theory that postulates an infinite universe. So, there's your degree of objectivity. Moreover, of course, the best system is still required to be true. There's an objective fact of the matter whether our universe is finite or infinite. So maybe that is all the objectivity the laws require, right? Like the system has to be true, and there's going to be a fact of the matter whether some system actually does meet what our standards of simplicity and strength are. So maybe that deals with that problem. Okay, let's turn to another problem. So suppose that we do settle on clear criteria of simplicity and strength. Even so, it may be that by those criteria there is more than one system that counts as the best. There may be systems that are tied as the best. So here's an example given by Ned Hall from the article Humean Reductionism About Laws of Nature. Imagine that far in the future, physicists have settled on two competing fundamental theories. We'll call them safe and sorry. Both of these theories make exactly the same predictions about all phenomena observed so far, and both of these theories are assessed as equally good in terms of simplicity and strength. Now, there is a possible experiment that could decide between these theories. This experiment involves a very powerful particle accelerator. SAFE predicts that if the experiment were performed, it would go smoothly and generate certain results that are analogous to the results we normally get from particle accelerator experiments. So SAFE predicts, we do the experiment, everything is normal. Sorry predicts that if the experiment were performed, it would cause a second Big Bang and destroy the universe. Now, given the enormous risk, it's decided that we're not going to perform the experiment. And if this sounds completely outlandish, I mean, this is actually analogous to how some physicists suggested in the early years of the development of the nuclear bomb that a nuclear explosion might ignite the Earth's atmosphere and destroy all life. I mean, of course, that wasn't taken all that seriously, but it was taken seriously enough that they had to sort of work out, they did some equations, right? They did some calculations and tried to work out the risk. So the sorry theory makes that sort of prediction. I mean, it seems like this could happen. This is one way that events might go, right? We might find ourselves in this position where we have these two theories and one theory makes this horrifying prediction. Now, so anyway, the experiment is just never performed. Now, since the experiment is never performed, both safe and sorry remain tied as the best system. Now, the intuition here is, well, either safe is true or sorry is true. Either safe or sorry describes the laws of nature, but not both. Moreover, there's a fact of the matter what would happen were the experiment to be performed. It's either true that were we to perform the experiment, it would go smoothly, or that were we to perform the experiment, the universe would be destroyed. We don't know which is true, but one of those is true and one of those is false. So, what do we say about this situation? Which is it safe that describes the laws of nature, or is it sorry that describes the laws of nature? Well, one option here is to say that in the case of ties, the laws of nature are those axioms that are found in each of the best systems that are tied. I mean, Lewis actually does suggest this in some places, that we just sort of take the intersection of the theories. So the laws are the intersection of axioms from both safe and sorry. But then what would happen if we were to perform the experiment? Well, I mean, obviously something would happen, but on this view, what would happen is not going to follow from any of the laws. Since safe and sorry make different predictions here, And since the laws are determined by the shared generalizations between safe and sorry, what would happen in this counterfactual situation cannot be determined by the laws. And if counterfactuals follow from the laws, it seems that it's simply indeterminate what would happen. So the counterfactual, if the experiment were performed, the universe would be destroyed. It looks like that's just neither true nor false, under the assumption that the experiment is never and will never be performed. So, yeah, because this thought experiment stipulates that the situation that would discriminate between safe and sorry has never taken place and will never take place. And so on the best system analysis, it looks like it's just going to come out that, well, nothing makes either safe or sorry true. There's just nothing that decides between them. On the best system analysis, remember, laws don't govern. Laws are just special kinds of regularities. But there is no, there are no regularities of the kind that would decide between these two theories. So the point is not just that we don't know which of them is true. Obviously, that's the case. The point is, well, we want to say one of them is true, but on the best system analysis, nothing makes either of them true. And so, in the worry is that seems like the wrong result. Hall presents another version of this type of thought experiment, which raises a slightly different problem. So again, we will suppose that we have only two competitor theories. This time we'll call them T1 and T2, both of which are equally good according to the best systems analysis. And again, the only way to decide between these theories is to perform an experiment with a particle accelerator. If we don't perform the experiment, then both theories will be compatible with all the evidence that there is or ever will be. But now suppose, in this case, neither theory predicts disaster, right? So in both cases, if the experiment is performed, we're just going to get the usual sorts of results that we get from particle accelerators. Well, here it looks like surely performing the experiment is a no-brainer. But Hall says it's very difficult for the best systems analysis to make sense of why we would perform this experiment. So as Hall puts it, should you decide not to run the experiment, then, and I quote, "It's not that you would be finding out about some basic aspect of physical reality of which you would otherwise be ignorant. On the contrary, if you forego this experiment, then you can be forever confident that you know all the facts about the fundamental laws that there are to know, namely that they are indeterminate as between the T1 laws and the T2 laws." So whether or not we perform this experiment, we will know everything there is to know about reality. If we perform the experiment, then we will learn that T1 is true, or we will learn that T2 is true, depending on the outcome of the experiment. If we choose not to perform the experiment, then we will learn that the laws are those generalizations shared by both T1 and T2, and that's all. And that what would happen were we to perform the experiment, that's indeterminate. Either way, we know everything. So there's no point spending all the money and time that would be required to run the experiment. And of course, the trouble is that this seems to be completely contrary to scientific practice. I mean, scientists would be motivated to perform the experiment, but how does the best system analysis account for this? So, I mean, there are a couple of options. There's a couple of things we might say. So one thing we might say here is just, well, we can perhaps account for the motivation to perform the experiment in other terms, right? So one of the goals of science is discovery and exploration, which includes creating new things. Scientists aren't interested only in finding out how the world actually works. They're also interested in making it do different things. Performing this experiment will create a new phenomenon. Maybe that alone can justify performing the experiment. Another response is given by Christian Lowe and Siegfried Jarg in their article, "What Humans Should Say About Tied Best Systems." They argue that if we perform the experiment, this will provide us with laws that are more unified. If we perform the experiment, it will become the case that either T1 or T2 states the laws. The experiment will sort of break the tie between these systems. So suppose we don't perform the experiment. Well, then the laws of nature are just the intersection of T1 and T2. That provides less information and is less unifying. Our basic theory of the world will have to state two incompatible theories and then take the intersection of both, which of course is, that's pretty unelegant, complex, and it gives us less information than either theory would alone. By performing the experiment, we eliminate one of the theories and can take all the axioms of the other one. So essentially what we're doing by performing the experiment is making the world more law-like. And that's a good thing. That's something we should want to do. We should want the world to be more law-like. Laws are, one of the achievements of science. Now, of course, this is an odd consequence, right? Like it's counterintuitive, right? We're saying that like we control the law-likeness of the world to some degree. Our decision to perform the experiment makes it the case that either T1 is the right, either T1 is true or T2 is true, right? By performing the experiment, we make it the case that there are either T1 laws or T2 laws. And yes, that is counterintuitive to say that we make the laws in that way. But remember, something to keep in mind here is that the whole point of the best system analysis is that the laws are nothing more, ultimately, nothing more than patterns of events and properties in the Humean mosaic. So with that in mind then, it shouldn't be surprising that if we do different things, we might end up with different laws. After all, we are part of the Humean mosaic. Yeah, there are very perhaps unusual situations, but very specific and unusual situations where we, by being part of the Humean mosaic, we do different, the things that we do determine what the laws are. That's exactly what the Humean would expect. So that's the best system analysis, and that's all I'm going to talk about for now. So I'll say goodbye and see you in the next video.